Next talk is on a versatile software solution for MIPI C-PHY testing. It's presented by Paul Willis of UNH-IOL. Paul has worked at the interoperability labs for about 4 years while attending the University of New Hampshire for electrical engineering. He is currently pursuing his Master's of Science degree in electrical engineering at UNH. He continues his work on MIPI physical layer testing and software development. So please welcome Paul. Paul.
Good? All right. So the introduction of me kind of got out of the way. Blake Brown was going to come originally, but I was open, and I've been working on the software more than he has, so it was decided that I should come in his place. So for the agenda, I'll just briefly talk about what is the IOL, since we're not really a big name brand. And then I will go over testing tool overview of what we've been working on. Then the actual physical test setup for people doing transmitter testing of C-PHY interfaces. In software, how you do clock and data recovery, since it's slightly different than how you do it in hardware. A demonstration of a packet decode, and then the transmitter tests I'll go through one by one. So we've been a member for a while, since 2007, and helped develop the test suite for DeFi, and also a DeFi GUI, which is a test tool that's available to MIPI members on MIPI.org. And I encourage anyone interested in doing testing in C-PHY to look at that as a reference implementation for how a CTS could be implemented in software. And we're currently an active test house for a few protocols and DeFi. We're active in the test work group, and outside of MIPI, we help other organizations develop new technologies and employ 100 university students. And if I believe correctly, we are currently allowed to do submissions to the test registry, product registry, which opened recently. So we thought there was a need in the industry for a software like DeFi GUI that's a reference implementation, because there's existing oscilloscope software implementations, and we don't really want to compete with that. But let's say you have waveforms from two different oscilloscope manufacturers. You still want to be able to use the same slicer, the same CDR, and the same measurement algorithms, so you can compare apples to apples the measurements you have, maybe across different implementations or different hardware revisions. So yeah, it'll be available to purchase to people who are actually members of the MIPI Alliance. And yeah, so we named the software C-PHY GUI in similar naming scheme as DeFi GUI. And it's based in MATLAB. It's just the environment that we found most suitable for doing signal processing. The primary purpose is to evaluate the physical layer transmitter characteristics, not RX, not protocol. So the first thing you have to do in making a software like this is import the waveforms into the software somehow. So we can load in saved waveforms from Tektronix, Keysight, LaCroix, and Rohde and Schwartz. And then also through a Visa implementation that we have, actually read data over Ethernet or GPIB. The other primary features being a decode, so that can be used in debugging and protocol layer tests. Actually show the results in a front end, and then also save them to a database that can be loaded later. And then a headless command line interface, so if you don't want to actually run the front end. So this is what the software actually looks like. So as you can see, these are actual tests that you'll see in the CTS as they're lined up here. We assume that there won't be more than 4 lanes in a single given implementation, but it's kind of semantics. You can just save and load databases. There's a toggle button for LP and HS mode, and then a button for actually starting the tests and closing all the plots at a single time. So this looks pretty familiar to anyone who's worked with Defo GUI in terms of how it's actually laid out. A button for switching between file and oscilloscope mode, a drop-down for choosing the manufacturer, and then the actual address. So for save results, that's like if you want to save a log file to disk instead of just using the database in the front end. And save plots if you want to save the images of the resultant tests. Byte decode, when that's checked, that spits out all the data to a console and also to the save results log, and truncate in the case of if you have multiple bursts in a capture, you want to choose one single burst to operate on. Slicer guess, now this one is kind of an interesting checkbox. That's for the, we ran into a case where when we were running the slicer, we would find 2 lines that would have the same voltage state, because our slicer just looks at the bit levels between strong and weak, and then also the 0 point. And if you have 2 lines that are the same, that's sort of invalid for C-PHY. So the slicer guess, it takes, when that's checked off, it takes the line that's most closely strong or weak 1 or 0 and assumes it's that, and the other one's the other state. And that helped us in actually not losing the state in software, which is something to be concerned about. And the failures you see, especially DVOD, which is a very sensitive measurement, or sorry, DVCPTX, I would say is most likely attributed to the termination board we're using. It was an early version of the hardware, and actually today they're testing the S parameters on a newer revision in New Hampshire, but I don't have any results for that right now. So an actual physical test setup for someone doing transmitter testing looks something like this. This is a block diagram. In the tests that we've done, we've been using the moving pixel P339 since it's a chicken or egg problem when you're developing software like this. You're not going to have any devices until you have working software, but you need some sort of pattern generator or traffic generator. And so the data lines A, B, and C go to a probing point, which could actually be soldered onto a termination board that you're using, and that would make it as close to the termination as possible. And that's desirable to minimize reflections that you might have along the SMA cables. And so you have high impedance probes and a real-time oscilloscope, and that's where you have your captures. And you either save, binary waveform files or CSVs, or just to run it over GPIB or Ethernet. So, like I said, in software, it's a little bit different than in hardware for doing clock and data recovery. The first thing we do is low-pass filter the data. So that gets rid of any, if there's a noise and you're wobbling around a 0 crossing, you're not going to get a bunch of crossings in a short period of time. And then you take the differential edge time. So you take your differential waveforms of A minus B, B minus C, and C minus A, and find where they cross 0. And the actual way you do that is by interpolating. Let's say you go from 7 millivolts to minus 3 millivolts. You'd say 70% along that time interval is when the actual 0 crossing is. So you build up a relatively accurate series of edge times out of that. Then you throw out edges that are out of spec from the UI, so if they're either too long or too short. So this takes care of cases like at the beginning of the burst, when you just have a long period of just basically 0 volts. You don't want to say that's a really long bit. And it also throws out any runt bits that might exist from leftover noise. So you find the mode of the UI length, so the difference between those edge times, and you say that's your nominal bit rate. And then you run the find edge code again using that estimated UI length and throwing out any data that was shorter than a half a bit or longer than 2 bits. And out of that, you build up a pretty accurate series of edge times, and then you can move either 90 degrees out of phase to say, okay, clock in the center of the bit, or what may be a better solution would be to actually do it at minus 20%, which the spec seems to imply is the correct time to clock the data. So for the encoder, currently we're just doing byte level decode. So unlike Defo GUI, it's not protocol aware for CSI2 and DSI. But in terms of just looking at the actual output 16-bit words, it's working. So it's unlike DeFi, you can't just look at the lines on oscilloscope and say, yeah, I definitely know what the data is. So in software, we just implemented a large lookup table for doing the mapping. And in general, you don't want to use long packets. Usually for physical layer measurements, you want long packets because you'll have a lot of data to work with. But if you're just trying to verify protocol behavior, a long packet will spit out a lot of information to the console and the log file. So this is what a cropped single burst of actual data looks like. And you'll notice nowhere in the CTS does it mention a waveform to use, a reference color bar pattern, like in DeFi and also in other specs. And the reason for this is that you have, since your data is not really directly mapped to what's going on, or rather it's not deterministically mapped what's going on the line, you're guaranteed to have a certain amount of transition density and a certain number of state transitions, regardless of the data. There's probably a small section, you could probably try to make an image that made it a stressed waveform that only had more state transitions than another. But in general, if you just use random data, it will work. Now, also, since this isn't exactly binary coding, you can't really just use the conventional wisdom of 0.35 divided by your rise fall time for what your sample rate should be. Since there isn't really a designated rise time or fall time in the CTS, and also you're going between arguably 4 different levels, you probably want to be a little more conservative with what you do for sample rate compared to symbol rate on your oscilloscope. And you also want a relatively long packet, so you have a lot of data to work with. 5,000 is probably on the high end. You could probably get away with a little less, but I wouldn't say less than 1,000 symbols for doing phi measurements. So now I'll go through the actual HS transmitter tests. So if you're familiar with the CTS, these should mostly look familiar. And so this is kind of, I guess, goes through them if you aren't familiar with it, and also how you would kind of make your own software implementation if you're interested in that. So TLPX is quite simply the same as it was in DeFi, where you have a trip level. In this case, it's 550 millivolts, and you just figure out the time between VA and VC, so data lane A and data lane C, crossing that trip level. And you'll do the same interpolation you would do for the clock data recovery to find the exact time. And T3 prepare is similar. There's an analog in Defo GUI where you just send 0 volts for a period of time before turning on your HS transmitter. And that goes from the end of TLPX until you first start sending a differential signal. And so there are 3 tests that verify the opening protocol sequence of the HS packet, and those are sort of configurable on the device. They can be a variable length, but they have a range of their length. So currently, we're only doing preamble, which just verifies the total length, but it wouldn't be too hard to implement that, and we plan on doing that in the future. And you know the preamble ends when you see the sync word, which is a very specific sequence of symbols on the line. So a lot of the amplitude, actually all the amplitude tests are based around building up an eye diagram. So clock to data recovery ends up being very important. And that's been the hardest part for us, is to actually build up accurate clock times. Because if you're not clocking correctly, you'll see lobes around here, and your data looks a little more muddy. And even this isn't perfect. it's a combination of the CDR being imperfect and also the RGB perhaps not being having the right S parameters that we would like. So you can clearly see, though, there's the strong and weak 1 and weak and strong 0. And you want to verify, if you used to call this 0% of a UI minus 20% on this built-up eye diagram, that your strong 1 maximum value, so right, if you just took a slice right there, the maximum strong 1 is in a certain range, and the weak minimum weak 0, so the bottom of this distribution. You can do the same thing for the outer edges of the weak 0 and strong 1. And DVOD, which is usually a very sensitive measurement, at least in terms of D-Phi, is calculated by taking your max strong 1 and then subtracting the absolute value of the minimum strong 0. So ideally, you want your HS1s to be the same amplitude as the HS0s, so there's no asymmetry in the bits and emissions due to data. And this plot, it just actually identifies where the maximum strong 1 and minimum strong 0 was observed in the waveform, in case you're curious about ISI. So VOH-HS is voltage output high, high speed. So you take the mean of this positive waveform, of the single-ended waveform, and you do this for all 3 data lines. And you just take the mean, so it's not a mode or maximum or minimum. And in case I didn't mention this earlier, on this slide, when you're doing VOD, you're doing all 4 of these measurements for all 3 differential pairs. So this, I think, was probably one of the more interesting slides. It's the common point tests. So the common point in C-PHY is similar to the common mode in other differential signals, where it's all 3 lines added together, then all divided by 3. And you can roughly assume that if you have a lot of common point, if your common point signal is large, you'll have emissions out in the system, which is something that's usually undesirable. So you calculate and evaluate the common point for each of the transitions, the 6 valid transitions you can have, or 6 valid states rather. And DVCPTX, so is that's the half the difference between the highest and lowest common point values that you see anywhere in the waveform. So as you can see, there's different frequency content. So we use the color bar pattern here just for reference. And you can see that when you filter it for between 50 and 450 megahertz, there is still the individual single-ended lines do have frequency content that differs depending on the data. But the common point, which is this blue in the center, is actually relatively constant and doesn't seem to be data dependent. So I thought that was something that's relatively interesting to see, whereas D-Phi, if you looked at a similar graph, your common mode emissions would be dependent on the data. So you evaluate this at DC, so sub 50 megahertz, and then bandpass filter for 50 and 450, and then high pass filter above 450 megahertz. And the reason you do this is because you're interested in different frequency emissions that you would see in your device, and they have different acceptable value ranges for each of them. And finally, you just verify that the last 7 symbols in the burst are the 4 symbol. And we haven't done anything with the LP tests, but it's my understanding that they are identical to D-Phi, or at least very similar. So implementing them should be very similar to implementing them in Defo GUI. So this is, I guess, how you would implement this kind of test if you were interested in doing that sort of thing. And yeah, that's, I guess I ended a little early. I'm sorry for that. But, are there any questions? No? So we've been using, the question was, is there a reference transmitter we've been using? We've been using the moving pixel P339, but we also have another traffic generator that we use, the SV3C by Introspect. So we haven't used any real-world devices for C-PHY yet, but those are the transmitters we've been using for doing testing.
Any other question? For Paul?
Have you made a new RTB that you are going to standardize?
Sorry, I didn't hear that.
Turn on the microphone.
Test, 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 test. One, two.
Okay. Is there a new RTB that you're going to standardize and require people to use?
So
Repeat the questions, please. And just repeat the question, please.
repeat the question. Oh, or are you asking me to?
Yeah.
So the question is there a new RTB that's being developed? Do I understand that correctly? Yes. So we developed an RTB several months ago just for preliminary tests, but it hasn't really been performing as well as we'd liked. We just did a new revision this past week, and we'll be forming S parameters and then performing more tests on it, and hopefully that'll be working better in the next coming months. So it's currently a work in progress.
Any other question? No, thank you. Thank you, Paul.
Yes.
Very good.